when he expressed surprise or just wasn't expecting it.
Yeah, just interesting.
And that kind of thing is interesting. The fact that in the first two trials, we saw essentially what was kind of looking like a pattern-ish. Although we had to jump here too. But something about those 2 digits, the double digits, make it. If you think about it, 3 to 7 is actually up by 4, where 7 to 10 is up by 3. So the bigger jump in the second trial actually, what more surprising to me was actually the drop from 15, 14 to 3.
Okay, I see what I did.
Than the 7 and 10. But the 2 digits would grab your attention, just visually would grab your attention more. But that's why I had you guys do it a bunch of times. I wanted to collect more data to see if there was some kind of underlying pattern at work in the coins. Now, Sonny, I love what you said. I love what you said about the football experience you had about how whenever you called heads, you ran. I would always call heads just to spite the coach. It's great. Exactly. But the idea is there an underlying pattern? Is there an underlying pattern in the coin flips? First of all, does it make sense they're going down? Does it make sense that the L2 numbers are going down, the Y values are going down? Why does it make sense that the L2 numbers are going down? What do you think? Why does that make sense? Go ahead, Benji.
Because I'm pretty sure we all know that it's a point, this 50-50 probability. So as it gets further from 1 and 2,
okay,
you know, a computer would expect, that becomes more statistically improbable, but still possible.
I love what you just said. I'm gonna, because of what you said, I'm gonna grab something else from my 243 class that might explain visually what you're explaining perfectly verbally. I'm gonna go to the first day. Starter coins.
I'm an English guy.
But that's okay. But you also nailed the mathematics of it. So here, what you have right here, just take this in. I'm trying to give you a mathematical explanation of what Benji just said. Each one of these cells has an H or a T in it. The H and the T is governed by a random number command. I'm going to have you guys use this at some point on a quiz, I think either next week or the week after, where you guys actually are going to generate random numbers between 1 and 6 to simulate rolling a die. I brought dice today. We'll see if we have time to get to them. I hope we do. The idea is, see that command right there? Ran between 0, 1. Every time I press the F9 button, it generates another random number, either a 0 or a 1. Okay, so essentially, what I'm doing each time, if I stop pressing the wrong buttons. No. Oh, hang on a second. Undo. What I'm doing each time I press F9 is I'm flipping 200 coins. So essentially, it's just like what you guys just did, except here's the difference. If you follow in a line, that would be like what you guys did. So in other words, HT would be someone that took 2 flips to get tails. That T would be 1 flip. That T would be 1 flip. HT would be 2. HHT would be 3. HHT is 3. So you see an awful lot of 1s and 2s and even a lot of 3s. Do you see any 5s, 6s, and 7s in there?
Yeah.
You do. Look. Head, 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 tail. There was one of the 8s. See? And no matter how many times you do this, you'll always find those strings of long H's followed by a tail. There aren't many of them.
Look on the bottom line where that's...
It's all tails. So these are all... Now, this is because I told you to flip till you got tails. If I said flip till you got heads, it would be right here. But if you look up here, you've got 5 heads in a row. You've got 5 heads followed by a tail. We've got 5. This doesn't have a whole lot of heads, but it's got a whole bunch of tails. So it all depends. Now, Benji's point, I'm going to go back to Benji's point, is that once we get far away from 1 and 2 and 3, we should see fewer and fewer and fewer. The assumption about coins, and this is what you always say, the assumption about flipping a coin is that it's 50-50, or that it's half and half. Now, nobody ever proves that. They observe that, and they say because the coin has 2 sides, it's 50-50. What you can actually watch right down here, this is the percentage of heads and tails in the data up top. It doesn't add to 100% because of a rounding error. Watch those numbers down there. What are those numbers always hovering around? They're hovering right around 50-50. They're never perfect. 56, 44, 45, 56, 49, 51. Say that again?
How many trials?
200 in total.
So if there were 10 million,
It'd be even closer.
Yeah.
It'd be even closer. But if there were 20, it'd be even further away. So what you have to do is on small, and this is something we're going to get into in the last 4 weeks of class together, you have to kind of make peace with the fact that when we say something is 50-50, it doesn't guarantee it's going to happen one, then the other, then the other, then the other, then the other, then the other. It means over time, you're going to see those things happen in that percentage over time. 54, 46 is not very close. It's off by 8%, basically, 4 up and 4 down. But when you average that across the board, how often do you see 30-somethings or 70-somethings?
Almost never.
Right, exactly. You never see that. You see high 40s and low 50s, almost inevitably. Okay? So Benji, thank you for that. I want to see if we can somehow observe that in our data. Okay? Did you guys, did you get a scatter plot of the data? Let's shut this down, for now anyway. Come back to it. Swing over here. Get this guy fired. I got the data entered in. All right, I got an L1 and L2. My plot on. I got to change my list to L1 and L2. There we go. There it is. Look like yours? Oh, sorry, I got a line on still. Let me turn it off. Still got the line from the last problem in there. There we go. Look like you guys?
Yeah.
Okay, there's no y-axis because we didn't have a 0. We didn't have a 0. That's okay. That's all right. Technically, we could throw a 0 in there if you wanted to with the 28, but we'll just leave it out. We can put it in later if you want to. Did you try to find a model for it? Good. What did you go with?
Quad.
Good. Nobody went with linear? I mean, could you throw a linear regression on there?
You could.
Of course you could, but Crystal's going to tell me you shouldn't.
Yeah.
It's not a line. It's not representing linear data. It would be an average rate of change. On average, how many flips is it going to take to get from here to here? But that doesn't tell us anything. That's not what's actually described in the data. So you use the quadratic. Thank you, friends. Let's do it together. If you haven't already, it sounds like most of you have. Quad rig. I'm sticking Y1 if that's okay with you guys.
Mm-hmm.
All right, there it is. Here it is. Yeah. Yeah.
I'm getting an argument.
Ooh! Not for me, you're not.
No.
See,
yeah.
real quick, that could be something very, very simple. Quad rig. No, not L1, Y1.
Oh.
There you go. Good. Okay, good. Who likes it? Who doesn't like it? You don't like it, Kirsten? Wait a minute, hang on a second. Shelly, tell me why you like it first.
Because I'm natural.
Oh, good! But why do you like it? Say, we have lin and we have quad. We have a linear and a quadratic regression. Why do you like the quadratic better than linear?
It just follows it.
You've got a curve in the data, right? You've got a change of slope. The slope is not consistent. In other words, every time we do a trial, we don't lose like 3 more people. We lose a bunch of people right at the beginning, and then we start losing fewer people as time goes on. When I say lose, you see how there's a negative slope going on here, friends? There's a negative slope. We're losing people as we go. We lose a lot of people up front, then we lose fewer people in time as it goes by. Does that make sense? We're losing people more slowly. Is it okay to say that? I'm second guessing myself on my English now. Damn it. I mean, I just said it. Is it okay to say it? Please, Ryan!
Because the difference between a quadratic regression and linear regression is because the linear regression is just a straight line.
Exactly, which is a constant losing people.
So it's not really complete. It's not completely accurate because it's not matching with.
Oh, brother, none of them are completely accurate. They're best fit, not perfect fit.
Well, no, I'm just saying the difference is like with the linear regression, it's not like going along with what the line.
Exactly. You could easily. Did anybody slap a linear regression on that, or did you not even waste your time? Some of you did. Good, and you don't do it, right? I'm guessing it's going to look something like this.
Yeah.
Something like that.
Yeah.
It's going to totally underestimate and totally overestimate, and then we'll do a crappy job. Good. Please, Benji.
I just got why we don't like it.
Wait, hang on a second. I'm not convinced we don't like it yet. Shelly, you like it. Who else likes it? No. Go ahead, Ariel. Tell me.
Looks like it fits.
It fits, right? It fits. Good. Andrew, you like it? Go. Oh, because it fits. So, given the choices that we have, hang tight. Hold that thought, Sonny. Hold that thought. I want to hear from you. I do. But I loaded the question a little bit when I started this. I said, given the choice of a linear model,
You want to argue it.
of a linear model and a quadratic model, which one do you like better? Clearly this one works better. I heard somebody say cubic model over there. Did you guys try cubic?
Yeah.
Oh hell, check this out. You ready? Go down your list of models. Stat, calc, go to cubic reg. Give that a whirl. What the hell? Why not? Please realize too that what you're doing with the push of a button right here would take any normal human being about 3.5 days to do by hand. Only because you're talking to a human being that actually can do it. And it's amazing that you can do this. Boom! Look at that!
That's even better.
Is it?
It looks like it does. It goes back.
Good, good. Hold these thoughts. Hold. Thank you, Hassani.
Oh, wait,
Hassani
no,
has
no.
found us a curve that fits the data very, very nicely.
Change your windows.
Yeah, hang on a second, Crystal. Hold that thought, because you're saying something exceptionally nice over there. So we have a cubic model. That's potential. Now that I set this loose. Anybody try something different? Please?
I want to do an exponential
You want to do an X? What the hell is that? So we're going to write down the list. Good. Thank you. Thank you. Check this out. Watch this, friends. Watch this. This is the beauty of technology. You just keep trying them all you want. Just work your way down the list. Okay, so let's try a stat. Let's go with edit, not edit, calc. Anybody try quart reg? That's a fourth power reg. So instead of x squared or x cubed, it's x to the fourth. Anybody try that one? No, we don't want to. Okay. There's another lim reg. You can leave that alone. The next one down is a natural log reg. This one's a weird one. This one tries to fit a curve that looks like this. You generally don't want that because the data's going the wrong way for that. Our data's doing this, not this. So don't sweat that. This one right here, exp reg. This one, exp, stands for exponential. I'm going to come back to this cubic model because I'm not ignoring it, friend. I'm not ignoring it. I'm going to come back to it. I'm not! I'm just trying to get all possibles. Exponential model.
There we go.
Let's try that one. And you know what we're going to do? I'm going to put the exponential regression in Y2, so we keep that cubic model that was in Y1. And
No, that's another one.
let's get like 3 or 4 of them going. Let's do the exponential regression and put, oh my goodness, and put it in Y2. Okay, whoops.
a one.
Good, good. Hold that thought. Hold that thought. Quick. I'm gonna do the quadratic regression again.
You're gonna error when
Hang on a second. Hang on a second. Quadratic regression again is going to be. I'm going to put that in Y2 for now. Okay, there she goes. Now here's the cubic first.
That's what I was doing.
There's the cubic. Here's the quadratic. Now they're very, very close to each other.
Yes.
They're extraordinarily close to each other. Let's talk about, I'm going to make one look a little bit different. Hang on, let me make one look a little bit different. I want to come down and make the quadratic darker.
I'm getting the error going.
Okay, there's your cubic regression. And here comes the quadratic regression. I want to talk about why each of those might not describe well, perfectly, this experiment if we kept the experiment going. If we refined the experiment, and we've done about 150, 200 trials total, right? But why would neither of those models do the best job? Now, I'm going to turn one off. I'm going to turn the cubic reg off for a second. I'm going to turn it back on in a minute. I'm going to go back to the quadratic regression that we liked so much in the beginning. And I'm not saying we shouldn't. There it is right there. Why does that not do the best job of describing what's going on with our data? What, Shelley, go ahead, go ahead.
Because it starts going up.
That's the problem with parabolas sometimes. The problem with parabolas sometimes is it might, because of the way parabolas are set up, they're symmetric. So as it comes down, it's going to hit a minimum or a maximum, depending on what you're graphing, and then it's going to go back up again. With our bike, what we just did, we ignored that part of the graph. We ignored it because I started at 0, 0. I essentially started at the vertex, and then traced out 1/2. The problem here is, based off of this data, it goes back up again. That can't be true based on what Benji said. So I'm not saying that, hold that thought. I'm not saying that the quadratic regression is a bad idea. I'm saying it might not be the best fit for this particular data because of the shape. I think we've ruled out linear models. Good. Let's go back to quadratic. Cubic 2.
When I try to do that other one, it gives me an error.
Hold on, there's a reason for that. We're going to come back to it.
Yeah.
A quadratic model's shape is going to either be a U or whatever upside down U is called.
I know, I was just saying
I don't know what that would be called. And I'm totally second guessing my English right now. So the problem with that is if your data doesn't do that, Your model shouldn't do that either. Now what you could do is you could move the parabola over, I guess, so that it bottomed out over here and then went back up further to the right. Can anybody see why that might present an issue? What does that assume? What does that assume? That my Excel spreadsheet just disproved, actually. Let me throw, what about the 50-50 in particular, Hassani? Thank you for that. What about the 50-50 of course I just turned it off, didn't I? Oh no, I didn't, here it is. Here's our data, right? If I do this experiment again, will it get the exact same data? No. Matter of fact, what could happen if we run this experiment again? Could anybody flip more than 9 could somebody need to flip 10 or 11 or 12 or 13? Theoretically speaking, you could start flipping at 9 o'clock and keep flipping until 10 and never get heads. Is it possible?
Yes.
Is it likely?
No.
No. But if you do the experiment over and over and over and over and over, you're going to start seeing this table begin to flesh out down here. Because they have to. Because of what Benji and Hassani are saying, that 50-50 means that every time you flip a coin, it's just as likely to come up tails as heads. Now, it's very unlikely, as we saw from the other Excel sheet, to keep getting a bunch of heads in a row followed by a tail. But it does happen. And as a matter of fact, some of those that you saw actually had 10 and 11 and 12. Not very often. But the more you do it, the more you see it, yeah? The more you do it, the more you see it. Okay, so, question now is, I don't think the parabola is going to work ever. Because of that. For this particular data, you see what I'm saying? I'm not saying ever. I mean, obviously it works great for the blank. But it doesn't work for this particular data because of that problem. I mean, we'd have to essentially have the problem be infinitely wide to account for all those possibilities. Here's my gripe with the cubic. It's a similar gripe. Go ahead, Stefani.
It flattens out when it goes down.
Right. Cubic shapes, cubic models do something more interesting. You might remember this in 95. I'm second guessing that too. I'm not sure. Cubics have an S shape. They tend to do this. Now that's a general shape of a cubic. The humps can be closer together or further apart, but in general, they've got two turns. Go ahead, Andrew.
Oh, I don't want to move ahead.
Go ahead.
Does that mean the exponential model will actually work the best? Because
Hold tight. We have to make sure we understand what that is first.
Okay.
Let's make sure we understand what that is. But we have to, and I want to make sure that you buy the equation before we see if it even fits. I mean, as we saw, the cubic model, let's put it back up there again. The cubic model fits great in the data, doesn't it? I mean, if you look at the cubic model, here it is in Y1. Oops, let's get rid of the quadratic model. No offense to anybody who liked the quadratic model. It did look pretty good for a while. And the cubic model looks fantastic. Look at that. But then what happens?
It drops off.
It does a little shuck and jive right here, and then drops. As a matter of fact, if we were to zoom in, right around the interesting stuff, I think something really cool is happening right in here. We'll do a real quick zoom, if it's okay with you guys. Let's see if we can see it. We might not be able to now. We have to keep zooming in. Oh, there it is. There's the shuck and jive. Now, it was hard to see when we were zoomed out. But the curve actually drops, then rises, then drops again. Is that what our data is doing? No. No. Our data appears to be falling off as we go. There is a hiccup at the end with the 9, but I think we could erase that hiccup if we do more trials. As a matter of fact, we'll check this model and get even more data and see how that works out. But let me zoom in a little bit further. I want to really exaggerate that hop. Did you guys ever use ZBox in 95?
No.
ZBox is pretty fun. There's the hump, and then there it falls off again.
It levels out and then goes.
Well, it doesn't actually. You can keep zooming in, and you keep zooming in, and it'll keep showing the hump. There is a high point in that hump. It looks like a level, but it's not actually a level. You can keep.
It's starting to drop more drastically than.
Exactly, and that's the asymmetry of the cubic model. So Linda, to address your question, if I keep zooming in, you're gonna see. So right now, what I just zoomed in on is that flat-looking line in the previous window. Now there's a flat piece here too, isn't there? But guess what? We can zoom in on that. You guys never use ZBox?
No.
It's kind of fun.
It's really
Super
cool.
fun.
So I'll tell you what. Let's go back out to zoom 9, And I'll show you how the hell you use it. So if you ever need to use it for anything, you know how to use it. Have you ever used a snipping tool in Windows?
Yes.
Some of you have. So has anybody never heard of snipping tool? Snipping tool? Okay, you all have. Okay, it's that. It's essentially that on a TI. This is one of the first things TI had before somebody else. Amazing. So what you do, you're here, and you're interested in this flat-looking line that's right there. We think it's flat. We're not sure if it's flat. You press your zoom button. Press your zoom button. Pick Z box, which is the first choice. Now this little tiny cursor appears in the middle. What you want to do is you want to use that cursor to draw a box around what you're interested in. So what I'm going to do is I'm going to scroll it down, 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 down. And you see this line that's right here? I'm interested in that line. So what I'm going to do is starting just, this is going to sound stupid because it's not mathematically correct, starting just above the line, which is not correct because it's not a line, but it looks like a line right now. Put the cursor not on the line, but 1 pixel above it. So do you see how the line is actually right there, right above the x-axis? Put the cursor right above that, the center of the cursor right above that. Now press the enter button 1 time. Now press down twice. Down, down. Now press right a bunch of times until you've drawn a box around that line that you want to explore.
Cool.
Now press enter again. And what it just did was, it just created a window around that line. But as soon as you do that, you realize it's not a line. There's a curviness to that wasn't being shown. Why wasn't it being shown before? Because the pixels are too fat and the curve was too small to see. Can you do it again? You keep zooming in. If you're interested to see where you are right now, press the window button. What you just did was you zoomed in on these y values right here and these x values right here.
Did you see the point where it comes down?
Say that again, Joe.
After the little hump, there is a point down there.
Oh, good. Let's get to it. Let's get to it. How many times do you have to zoom in, Joe?
Twice.
Twice. Okay, so let's zoom in again.
Out.
But you zoom out. Hold that thought. I want to come back to that. So let's see box it again. Maybe I'm interested from here. So I'll draw a box around here. How's that sound? Because once again, Linda's going to say, oh, there's a flat point there. Well, I don't know. Is it flat? Some curves do have flat sections, or flat-ish sections. This isn't one of them, though. This isn't one of them, although it shows a bit of a flat point right here. It shows a bit of a flat point. So what I'm getting at is that this, upon inspection, isn't the correct shape model either. Fair enough? Now, the one I think we want to look at would be an equation that starts at a given value, then drops more, but doesn't drop as much the next time, and then drops, 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 and essentially keeps dropping and never going back up again. That's the problem with the polynomial models. These are polynomial models, as are the linear ones. The problem with those are, they don't have that limiting factor. Benji, go ahead.
That was my coolest thing about when it's like the probability that it'll take 10 million tails before you get heads.
Yes.
Is never 0.
Oh no!
The probability that
Why is it never 0?
Because it could happen.
But why is it mathematically never 0? It could happen. What's the chance that it happens?
Infinitesimally small, but not.
Give me a number. Did you hear what Benji just said? It's quite important.
1 out of 15 trillion.
And where did that 15 trillion come from?
I said random.
Check this out. Check this out, friends. Check this out. You've actually nailed it, Benji. You've nailed the model we need to use. Check this out. Okay. Let's approach this mathematically first. Then come back. Hold that thought. We started this experiment with 28 of you in the room. Correct? So at the start of the experiment, Twenty-eight of you started the experiment. I said, all of you flip a coin, stop when you get tails. How many would we expect to be out in the next round? Half of them, right? Because on average, as we just saw on that Excel sheet, half of you will flip heads, and half of you will flip tails. Now look at our data. Look at our data. It's a little noisy, but 15, 14, 7 was definitely low. And this is where I shouldn't have lumped them all into one trial here. Because now I can't look at the overriding thing. But we would have expected, after the first flip, we would have expected half of 28 or 14. Is that fair? Now those 14 are done. They stopped flipping because you got your tails. For those that, the other 14, right? How many would we expect to be left flipping after the second flip? Half of those, correct? So you'd expect half of 14, otherwise known as half of 28. Fair? Which would be 7. You'd have 7 left that said, I keep flipping heads. Fair enough so far? How about after the third flip?
After that, which is not a whole number.
It's okay, on average. We're talking about averages. It's okay to not have a whole number on average. So after that, you would expect half of 7, otherwise known as half of 28, which would be 3.5. Are you starting to see a pattern of what we would expect? We would expect after a certain number of trials, we would expect to get half of the remaining value that we got the previous time every time. So in other words, it never gets to 0, which is why we're getting an error on our TIs. We'll fix that momentarily. Your data did get to 0, correct? Remember how your data zeroed out? That's a problem. It doesn't, if you're trying to use this model, which is the exponential model, check this out. This exponential model that's right here, they look kind of quadratic. They look kind of quadratic. Okay, let's go up with this. There are 2 kinds of exponential models, and we'll just give a quick introduction to them today. We'll come back to them on Wednesday. There's exponential decay, and there's exponential growth. You're seeing, in this one, what do you think?
Decay.
You're seeing decay because we're losing data. Growth would be like bacteria in a petri dish or the population of the US, both of which I have data for. We'll play with next time. So right now, you can have a model like this. The trick about these exponential models is, it looks kind of quadratic, doesn't it? Looks quadratic. It curves like a quadratic curves. But the difference between this and a quadratic is what will this not do?
Never hit 0.
Well, it will never hit 0, first of all. Good, thank you. It won't touch the line, and it won't go back up again. It'll just keep getting closer and closer to the x-axis, which is kind of silly, but it explains what Benji said perfectly. He said, there is a chance it will take us 1 trillion flips to get tails. But that would be so far down here that it's essentially touching the axis.
And
It's not
a
mathematical.
trillion alternate universes.
No. In this universe,
Yeah.
it can happen. It can happen. It's just that it's not likely to happen. So that would be exponential decay. Exponential decay. That's the model we're looking at right now. You can also have exponential growth. You can also have exponential growth, which essentially looks the same, but it's flipped around this way. And then it rises. I don't like that. Exponential growth. Now, who wants to hazard a guess as to why the word exponential is in the title of this thing?
Exponents?
Where are they? I don't see them.
However many times it takes.
Look at how I rewrote some of those data points, right? Check this out. I'm going to rewrite this data in a more concise way. Okay, so I'm going to write it as x equals number of you left flipping. I'm going to redefine the variable a little bit to make the exponent pop out. Okay, and then this is going to be number of number left, or excuse me, number of nope, sorry. Number of trials. Number of you left flipping. Sorry, because you guys are the y variable. You guys are what we're studying. At 0 trials, which means basically I give you the coin and say, get ready. There are 28 of you. After the first trial, we take that 28 and multiply it by 1/2 to get the 14. Then you 14 are done, but the 14 that are here are still playing. We then go to the next trial, and we would expect 1/2 of that 1/2 of 28, which would be 28 to the 1/2 squared power. There's your exponent that Dai picked up right there. So that's where you get your 7 from. And then each trial after that, you get 28 times 1/2 cubed, 28 times 1/2 to the 4th for the 4th trial, 28 times 1/2 to the 5th, to the 6th, and then for the nth trial, you slap to the nth power. The reason why we couldn't get a model to fit while we were getting the error in the exponential model is that y value can never hit 0. Because taking a half of a half of a half of a half of something never actually gets to 0, but we had 0, didn't we? So what we'll do next time is we'll do 2 things. We'll flip the coin some more and keep adding to our data and try to get it to show up better. And then we're going to restate the data in a different way and try to get these zeros to vanish. Just by doing more trials. So you see this one right here, the 8 flips, there were no that had 8 flips. We're going to do it a few more times so we can get somebody that does get 8 flips to fill the data in. That's causing the problem right there, is the 8 to the 0. The TI isn't smart enough to deal with the 0. So we have to come at it on its own terms. We have other tools we can do besides that. We'll come back to that on Wednesday as well. But I won't see you guys again for Wednesday, huh? Yes, that's it. So we'll have the one quiz for next week, left over from this week, essentially. There's a quadratic modeling quiz up. I wasn't planning on Monday being off, though. I totally forgot about that. Can you guys bring questions on quadratic modeling for Monday? For Wednesday? Exponential modeling is great. We'll get into it more on Wednesday. I bet we will. But can you bring questions on quadratic modeling for next class? Please, Ariel.
There's an exam on the schedule, or are you gonna bump that?
Is that week 7 already?
Yeah.
Oh, I gotta push that back. I'll push it back.
Oh,
yeah, I'll push that back. Yeah, I'll push that. Thank you. I'll shove that back. Yeah, I'll shove that back to week 8.
Big relief.
Yeah, let's shove that back to week 8 for sure. Thank you for saying that.
Thank you for moving it.
No, because I would have talked about it on Monday.
Not this one.
We're on Monday.
This one.
So yeah, we'll move that. Make a note still.
This one here. The one with the square where we're doing.
What's that?
Where did that? The mid and.
What does something?
These wear
In the
socks.
United States.
Oh, I can't do it.
It's on the schedule.
Can't do it. She's playing there quick. And grab the quiz from in class if you want to fix it up. And bring it back Wednesday. That's totally fine. The one that we were talking about before with the bike.
Quadratic.
Take that back and fix it. If you want to bring it back on Wednesday, that's fine.
Is this?
Sure.
Either.
It's posted for this week, but I'll push that back to Wednesday.
Okay.
Because we just finished quadratic progression
Go
today.
ahead.
I think I thought I made a note on the schedule, which I might not.
Okay, can I ask one more question? So here, would this be 11.189? When I'm taking it out?
It was half a second before 12.289, so 11.789, I guess. 0.5 from that. Right, 0.5 from that. This one will be 0.1 from that. That will be 0.001 from that. That will be 0.0001 from that. And so forth and so on.
So is like the data slide.
It is right here. I can email it to you, Chris. It's not online, and I've lost it, except for the fact that it's still here.
Sorry, Mr. Rule.
Uh-huh.
And
Sorry.
thank you.
Sorry for what?
Well, the wording.
No. It was good to know. I mean, again, thinking mathematically is definitely different than not thinking mathematically. I'm glad you guys told me. I just wish it's a shame because it got in the way of the math. That's what drives me insane.
So this quadratic one was possibly due today, but you're pushing that one back.
Yeah, this is what
Yeah.
everybody
Okay.
turned in today, right? Yeah. And then this is turned in.
Did you do the quadratic one? I just
Yeah.
want to see if did you do the quadratic one?
Let's demand.
Yeah.
Let's look at that because
Because
I'm not
I went to the
happy.
tutoring lab,
Me too.
and we had a hard time finding the men in the United States in
You
2011.
know what? I just pulled the first one out. I'm sure our answers are going to be different with that. Because he's gonna Google something different than you and I did.
Okay.
You guys got it? Coming to you.
Okay, I want to make sure I did it right.
Because this.
Oh, yeah,
Hang on, give me 2
you ready?
seconds. You always think that you're. I have everything all over today.
There it is.
There we go. Okay.
Okay, so,
So I came up with these numbers in my calculator.
checking it.
There it is right there. And there it is right there.
Okay, we're the same.
We're the
Okay.
same.
All right.
And I did 124 and I did 122, or I did 123, if I rounded it up.
Alright.
So we're good with that. Now C, oh my God, 155, we're so close. That's it.
Okay,
So we're really close to that. I got 155,
I got 1539.
okay.
Okay.
Really super close. And D,
So this is where we got a little confused.
oh,
What to take to. Okay,
Here we go.
Okay, good, you did
We
this.
did the same thing.
Okay, but I did
But
3,000.
see this, that's because you looked up something different than I did. We looked up something different.
I did how many people, what was the population?
I did the population, but then I took half of that because of half of men, when I looked up the US
That's what I didn't
Census.
do right.
And then I took half of the men.
Because that's what I did right. I did, where's my where's my population? Where's, okay, right here.
Okay, and you have to take half of that because half of men are men. Population.
Sweetheart, you can't rely. Yeah, so you came up with
I came
that.
up with that, but then I divided it.
Okay,
See, I
so
did
that's
half
what I
of
did
men.
wrong. Okay, so let me. You don't want to.
So I said Google US Census population estimate of July 4th, 2011. And I did that and then I divided it by 2.
Okay, divided by.
I should give you my number so
Well, 1 half, yeah.
Right.
Let me give you my phone.
That would be so, I'm already getting lost last night, and he told me last night and it started freaking me out. I was like, I know, I had no idea.
Here. So I want to take that 150, 215,
I was like, no, my watch is school, I don't know.
We're still recording.
and
Whoops.